Dear friends, dear colleagues, it is my pleasure to welcome you to our today's optimization seminar. The speaker of our seminar today is Lieven Vandenberghe from UCLA. It is 6:30 in the morning in California. So thank you for being with us so early in the morning. So Lieven received his PhD from Leuven in Belgium, and this was followed by a postdoctoral position at Stanford University. And since '97, he's at UCLA, where he is now on a joint appointment of the Department of Mathematics and of Electrical Engineering. He's working on different topics of optimization with a certain relevance and impact in engineering, in particular in systems and control, signal processing. And so I want to mention the book he co-authored with Stephen Boyd, who is one of the, let's say, most prominent works in complex optimization. Today, he will talk on SDP and proximal methods. So it's a very hot topic. Thank you for being with us. We only have 45 minutes for the talk.
Yeah, thank you, Radu. And thank you for organizing and this seminar series and for the invitation. So the talk will be about Bregman first-order proximal methods for certain types of structured semi-definite optimization. It's joint work with Xin Yang, who's a current PhD student, and Suzy Chao, who finished recently. So to motivate the topic, we can look at the standard form of a semi-definite programming problem with an n by n symmetric matrix variable x. It has to be positive semi-definite, m linear equality constraints on x, and we are minimizing a linear function of x. So the most common methods that are used in general purpose packages like CVX are still the interior point methods that were developed over 20 years ago, and implementations that are also in most cases developed 20 years ago. And it's well known that these implementations don't scale well, at least for dense problems. And the exact complexity is a little complicated because there are two dimensions: m, the number of equality constraints, and then n, the size of the matrix. But if you look at the cost per iteration, then it involves computations with a complexity of m cubed, m squared, n squared, mn cubed. So if m is of the same order as n, it would be n to the fourth. If m is order n squared, which is possible because you can have order n squared linearly independent equations in a matrix variable of size n, that would be n to the sixth complexity. So in large problems, that's too high. And another problem is that customizing an interior point method to exploit problem structure is difficult, or the opportunities for exploiting problem structures are limited. So for larger problems, the first immediate alternative that comes to mind are the proximal first-order methods like ADMM or primal dual first-order methods. In methods like ADM, exploiting the structure in the linear equations would be much easier because you just have to solve, for example, a sparse linear equation that's formed from the matrices A, or in other methods, just apply the linear operator or its adjoint. There's still the issue that in splitting methods, part of the alternating optimization will involve a decomposition on the positive semi-definite cone. And in general, projecting on a dense positive semi-definite cone would require an eigenvalue decomposition, and that also contributes a term n cubed in the complexity. So to be more specific, we can look at two classes of problems that were actually the earliest ones that motivated the work on semi-definite optimization in the 1990s. A first class of problems were problems that involved relaxations of polynomial optimization problems or graph optimization problems, for example, the max cut problem. And those are lead to very sparse problems. so where the coefficients in the problem are all very large and sparse matrices. And for example, because they inherit the graph structure, the sparsity pattern of the graph of the problem. So if you look at the max cut problem as the simplest example, then the objective, the equality constraint just involve the diagonal. You have n of them. The objective has a sparsity of the graph. So in this case, the complexity of a general purpose interior point method would be n to the fourth, because m is equal to n. It's in this case very easy to exploit some structure and to reduce that by n cubed by a simple customization of an interior point method. And in this case, we see if we take a standard approach based on a splitting method, we would still have an n cubed cost per iteration because of the projection on the positive semi-definite cone. So in this case, which is admittedly a very simple problem, you actually don't gain by going to a proximal methods per iteration. Of course, it could be different in more complicated problems if you have more complicated or additional constraints, but in this case, the complexity per iteration would be on the same order. And in fact, a splitting first order method would require many more iterations than an interior point method. A second class of problems that motivated the interest in semi-definite optimization in signal processing and systems and control leads to a very similar conclusion. So many of those applications were motivated by the semi-definite representations of sets of non-negative polynomials or trigonometric polynomials or matrix polynomials. And the simplest result of that type is the constraint that a non-negative trigonometric polynomial is non-negative. So here the xk's, x1 to xn would be complex numbers, x0 is real. And the constraint is that this trigonometric polynomial of degree n is non-negative for all omega. So that's a constraint that can be represented by a semi-definite optimization constraints. So we'll see the details later. The dual cone is actually the cone of positive semi-definite Toeplitz matrices. And results like this, the fact that there is this exact semi-definite representation of this constraint was a source of many of the applications that were developed in the 1990s. More recently also, there was actually, again, more interest in these constraints in so-called grid-free compressed sensing, so extensions of the compressed sensing from where semi-definite representations play the role of the L1 or linear programming representations in the standard compressed sensing, and many extensions in control and to more complicated problems. But again, if you look at this as the simplest constraint of this type, then this semi-definite representation of the trigonometric polynomial or exploiting Toeplitz structure in an LMI on the dual side, then again, we will have n to the fourth per iteration in the general purpose interior point methods. Again, you can customize that somewhat quite easily to reduce it to n cubed per iteration, which is already much better, but often still too high for large n. And then again, for a proximal splitting method, where we use a standard proximal method, you would have order n cubed because part of the iteration would involve the projection on the dense positive semi-definite cone. So those two examples will be also the ones that we'll discuss in this talk. And the motivation is that in the literature on proximal methods, of course, there's a very elegant and nice alternative or other possibility, and that is to replace the standard proximal methods by a Bregman proximal method that would be matched more closely to the structure in the problem. So the goal would be to look at actually these two types of applications and see if we can reduce the order n cubed cost per iteration to something that's lower. So that's the motivation for the talk. And then I'll first have some introduction, some notation, and some facts about generalized Bregman distances or divergences. And then we look at these two applications, the trigonometric polynomials and then sparse positive semidefinite optimization. So proximal methods, of course, derive their names from the proximal mapping, which is defined like this. So it maps a vector y to the solution of this regularized least squares problem, where we add to function f the squared Euclidean distance to y. So it extends the Euclidean projection on a set C. If f is the indicator of a set C, then this is just Euclidean projection. And Moreau has shown that if the function f is closed and convex, then this always has a unique solution for every y. So even if f has a domain or f can be non-differentiable and so on. And then that's used in many types of methods. In the proximal point method, we just repeat the proximal mapping and run this fixed point iteration. So that's the proximal point method, or the that includes the augmented Lagrangian method. The proximal gradient method shows why it comes up very naturally. So if we have a problem where the objective can be split in a term f of x that has a simple proximal operator but can be non-differentiable, g is differentiable, then in the proximal gradient method, you first apply the gradient step to the differentiable part and then the proximal operator for f. And if we substitute the definition of the proximal operator and expand this definition, we see that is a very natural way of approaching this problem, because we keep the function f of x exactly. We make a linear approximation of the differentiable term, and then we add this penalty term that comes from the distance. So you can think of the penalty term also as a very simple approximation of the remainder of the linear approximation of G, for example. And then there's the proximal splitting methods that are all related to the Douglas-Rashford splitting methods and ATMM Spingarn's method and so on. And then the primal dual methods, Chambolle-Poc method and so on. So in the Bregman Proximal method, we replace the Euclidean square distance by a generalized distance. For example, in the gradient method, that would mean that we try to we replace the squared Euclidean distance by a generalized distance d, that will denote by d. And the potential benefits are actually first that by choosing a different, maybe better approximation, a term d that fits the structure of G better, you might be able to reduce the total number of iterations in the first order method. So then it's called some kind of preconditioning. Another potential benefit is that the proximal operator might become cheaper, less expensive than when you use the squared Euclidean distance. And in this talk, actually, the second motivation is actually the most important one that we'll try to exploit. So what is a generalized distance, or a Bregman generalized distance? Is derived from a Bregman kernel. So you have a convex function phi, which is called the kernel function. Convex function phi, we assume it's differentiable. In general, we'll have a domain that's restricted. That's not the entire space, because in many applications, the goal of choosing phi is to implicitly include some of the important, difficult constraints in the problem. So in general, it'll be often important that phi has a domain that's restricted, and the behavior of phi on the boundary is also important. And then the distance generated by phi is defined like this. You take the straight line here is the linear approximation at a point y. That's a lower bound on phi by convexity. And then at a different point x, we take the difference between the function and the lower bound, and that's the generalized distance. So it's not a real distance because it's not symmetric, but it's always non-negative because of convexity. And if you look at the definition of D, we see that D is defined for all x in the domain of phi, and for all y where the gradient is defined, so in the interior of the domain of phi. And the domain itself may or include the boundary, or a subset of the boundary, or no points on the boundary. Many other properties may be required depending on the algorithm, and they're sort of discussed in details also in the book by Sensor and Xenios. And then we can, if we use that to define a generalized proximal mapping, in at least the methods we'll discuss, the extension would be defined like this. So we take the function f, if we define a proximal mapping of a function f, we add a linear term with the general coefficient a, and then the proximal, the generalized distance between x and y. And if we use the squared Euclidean distance, then you can actually combine the linear term and the point y at which you center the distance, and write it as a standard proximal operator applied to the difference between y and a. In the general case, you cannot really combine it and write it as a distance, so we keep a and y separate as two arguments of the proximal operator. So it's also easier to just spell it out actually than to have one notation. But this is the operator we'll need. And in the general standard case, we know that this always exists and it's uniquely defined for every y and every a. For generalized distances, it's much more complicated to give general definitions. But the applications where we'll be interested in using this will be applications where we have a fast or an inexpensive algorithm for solving this minimization problem. And actually, almost as a byproduct of that algorithm, we'll get the properties that the minimizer in this optimization problem exists for every choice of A and every Y in the interior of the domain of the kernel. And also that the solution of this problem is in the interior of the domain of the kernel. That will also be important because typically the solution X will be used as Y in the next iteration of an algorithm. So those first properties are immediate in the standard case. In the generalized case, they're actually much more complicated, but we'll also only be interested in applications where actually we also know a simple algorithm for computing this, and then sort of it's not needed to say something in general here. So to illustrate this, we can look at the most standard case that is most extensively studied in this literature. It's a relative entropy. It's a Bregman distance generated by the negative entropy on the non-negative orthant. So H should be phi here. Generates a relative entropy as a generalized distance. So it's defined for every y that's strictly positive, every x that's non-negative vector, if we define x log x to be 0 for x is 0. And if you take the generalized projection on the hyperplane, 1 transpose x is 1, then we have this very simple closed form expression that can be evaluated in just order n operations. So it's somewhat cheaper than projecting on this set in the Frobenius, in the Euclidean norm. And we see also that this result, this closed form expression for the generalized projection, is defined for every choice of A, the linear term in the argument of the generalized operator, for every positive y, and the result is always a positive vector. So those are the properties that you'll need. And if you look at the contour lines, it's clear why. So this is the unit probability simplex in R3. So the intersection of the non-negative orthant with this hyperplane. This would be the contour lines of the distance, the relative entropy around a point y. We take a general arbitrary direction A, then we minimize the solution of this minimization problem will always be a point in the interior of the set. And that's because the entropy, negative entropy, will have has an infinite slope near the boundary. So if you solve this optimization problem, you'll never get a point on the boundary, even though the kernel function phi and the distance are finite on the boundary. So you get these properties. So these questions will come back in the applications I will consider. So now in the main point of the talk, we look at these two applications that I mentioned in the introduction. First, the non-negative trigonometric polynomials. And the question is, can we, by choosing a different Bregman distance, reduce the cost of evaluating a proximal operator compared to the Euclidean case? So the purpose here would be to look at convex optimization problems that include a constraint that the trigonometric polynomial is non-negative. So here, for simplicity, we'll take the polynomial to be have real coefficients. It could have a complex coefficients and then include sines and cosines, but for simplicity, we'll take it real, and actually everything extends to the complex case. So the cone of trigonometric polynomials that are non-negative, or the coefficients that are non-negative, is a closed convex cone. We'll normalize it to get a bounded set. So a convenient or a natural normalization is to take the first coefficient to be 1, because that also normalizes if this is a power spectrum, it normalizes the total power. But other normalizations are possible, right? You can have an upper bound x0 less than or equal to 1, or assume that in the objective you have a term that involves this quantity. So as I mentioned, this constraint that the polynomial is non-negative has a semi-definite representation. That is the reason why semi-definite optimization problems arise in these applications. So the semi-definite representation is this. So a polynomial has this, the coefficients have this property if they can be written as the diagonal sums of a positive semi-definite matrix. So the same cone can be written as the image of the positive semi-definite cone under this linear mapping D, where we map a symmetric matrix of order n plus 1 to a vector by taking the trace of the matrix as a first component, then the sum of the diagonals, the sum of the elements on the first diagonal, the second diagonal, and so on. So that's an exact semi-definite representation of the same cone of non-negative trigonometric polynomials. And the dual cone is the positive semi-definite cone of positive semi-definite Toeplitz matrices. So that involves the adjoint of this mapping, which maps a vector to the symmetric Toeplitz matrix with the coefficients of the vector on the diagonals. So we'll use this not in the next few slides. D and T will represent these two mappings: the diagonal, the vector of diagonal sums of the matrix X, and then the Toeplitz matrix. So if you look at, so of course this also shows why it's expensive to deal with these constraints in semi-definite optimization, because you introduce this matrix X of size n plus 1 and as an extra variable, just to be able to represent these constraints as a semi-definite constraint. So if you look at possible candidates for kernel functions for handling this non-negative trigonometric polynomial cone directly without going to the semi-definite representation, then maybe the first one to consider is the Kullback-Leibler divergence, which would be this kernel in sort of analogy with the relative entropy for the Rn for the non-negative orthant. If we look at the contour lines for n is 2, so this is actually a slice of this positive of this cone K, where we normalize x0 to be 1, and we just look at x1 and x2. Then we get this convex function. It's actually finite on the boundary of the cone, except where x is 0. It's actually easy also quite, there exist efficient methods for projecting, doing the generalized Bregman projection using this kernel function that occur in some applications in speech processing, for example, or are explained in books on speech processing even. But the contour lines also show why in our applications it's actually not satisfies the conditions we'll need, because the contour, the function doesn't decrease. The derivative can be bounded on the boundary. So if you use this in a projection or a generalized projection, you may get a point on the boundary. And in the algorithms we'll discuss, we'll need the generalized projections or generalized proximal operators to always give a result in the interior of the cone. So we won't use the Kullback-Leibler kernel, but the what's known as the Itakura-Saito kernel in signal processing, which is defined like this. There's also a convex function of the coefficients x. It's finite on the boundary of the cone, except when x is 0. And then it does have the same property that we had with the relative entropy in the Rn plus 1, where the in Rn, where the gradient of the kernel function goes to infinity as we approach the boundary. And therefore, also, if you use this in a generalized Bregman proximal operator, the result will always be a point in the interior of the constraint. So in convex analysis, would say this is an essentially smooth function, and this isn't. So that's why we will use the Itakura-Saito distance as a kernel. And then the question is, how expensive is it to evaluate this kernel function and its gradient? What's the distance, and what's the cost of using of computing projections, generalized projections with this distance? So that's the topic of the next few slides. There are actually a lot of connections between these types of functions and convex analysis and convex duality and semi-definite optimization. So if you first look at the cost of evaluating this function, that can actually be expressed as the solution or the optimal value of a semi-definite optimization problem like this. So if you fix x, x is the vector of coefficients of the trigonometric polynomial f of x. These two constraints give us the semi-definite representation. It says there exists a semi-definite matrix capital X, and the vector of coefficients of the polynomial is the vector of diagonal sums of that matrix. So those are the two semi-definite representations. So if you maximize the 1-1 element of that matrix, for example, by maximizing, just maximizing the 1-1 element, here we start with index 0. So the top left element of x, then it turns out that at the optimum, minus log of the 1-1 element is the value of this kernel function. So the optimal value of this problem here, this convex problem, with the matrix x as variable, and for fixed, the lowercase x is fixed here. If we fix x, that we get the optimal value of exactly this kernel function. It's also known, a very classical result is that the optimal x in this problem will have rank 1. So by maximizing the 0-0 element, we get a rank 1 solution. And then, of course, minus 2 log b0 would be the cost function. The b here is known as the minimum phase spectral factor of the coefficient vector x. Meaning if you form this polynomial of with coefficients b, you have a polynomial that's in z inverse that's non-zero for a z outside the unit circle. And so this is a semi-definite representation. In practice, there exist very efficient methods for solving this directly. And one very classical method is to directly substitute for x the rank 1 expression. D again is the vector of diagonal sums of this matrix. So this is a set of n+1 quadratic equations in the coefficients b. Right? So the first one is just the sum of the bi squares is equal to x0, and then you have the n+1 quadratic equations like this. And one can show that Newton's method for solving this set of quadratic equations converges globally to the solution. And that's one of the classical methods for calculating spectral factors. So this gives us the optimal value of the optimal value of this problem gives us the kernel. Here x, the vector x, is the right-hand side in equalities. So by taking the dual of this convex problem, we'll get another expression for the optimal value for the kernel function. And also by convex duality, we'll have the gradient of the optimal value with respect to the right-hand side, with respect to x. So if you look at the dual of this problem, we get something can be written like this. We have a dual variable y, a vector, which is actually the multiplier, the Lagrange multiplier for constraints, a linear term, and then this psi function is this function of y. So it's defined for all y that define a positive definite Toeplitz matrix. If you construct a Toeplitz matrix with coefficients y, you get a positive definite matrix. And this function psi is the 1, 1 element of the inverse of the Toeplitz matrix. So E is just the first unit vector. So this picks the first element of the inverse. And then the log of that turns out to be a convex function of y. And it's up to signs, some changes in sign, the conjugate of this kernel function. So this is a dual of this first problem on the previous slide. So the optimal value of this problem is still the same kernel function. And also the optimal value of y is actually the gradient or the negative gradient of the kernel function. So by solving the dual problem, we find the gradient of the kernel function. And from the optimality conditions of this primal and the dual problem, if we skip the details, we get the relation between the primal solution x, which is rank 1 with the spectral factor b as gives us the solution, and the dual optimal solution y are related by these equations. So a Toeplitz matrix constructed from y times the vector b is this E vector. And these are the known as the Euler-Walker equations in signal processing. So if y is given and you solve for b, this is known as the Euler-Walker equations. They can be solved by fast methods by exploiting the Toeplitz structure in T. But you can also fix b and solve for y, and you get also a set of linear equations because this is a Toeplitz matrix. The standard method for solving the equations, if y is given and you solve for b, is of one of the early methods is the Levinson algorithm. It has an order n squared complexity. There's also a reverse version of that algorithm where you fix b and you solve for y. And that is very much just the same Levinson algorithm but run in a backwards mode and also has an order n squared complexity. But the conclusion is that given the primal solution b, the spectral factor of the coefficients of the trigonometric polynomial, we can compute this dual solution by this reverse Levinson algorithm, and that gives us the gradient of phi. Finally, the kernel or the distance itself is known as the Itakura-Saito distance. So if you would be defined like this, if you use the definition of the Bregman generalized distance. It's been known, at least since the 1970s, as a spectral distance measure to compare power spectra in speech processing. So we'll be interested in computing the generalized projection on a hyperplane, where we take this hyperplane, this is sort of the natural equivalent of the, in the probability simplex, normalizing the sum of the components to be 1. So again, the notation of the Bregman distance proximal operator is a little complicated, but if you write out the definition, this is what we need to do. We have a linear term, the distance from x to y, and then we project on this hyperplane. So if you just combine the linear terms in the distance with the linear term in the inner product, then we get this optimization problem where we have a linear term plus the kernel phi. So the question is, what's the cost of solving this optimization problem with this entropy kernel phi if C is just an arbitrary vector? So we have one equality constraint here. It's an unconstrained problem with one equality constraint. So if you introduce a multiplier lambda for the equality constraint, we get a problem that involves this dual function that we discussed. So it's a dual a convex optimization problem in a scalar variable lambda. And the first term is a convex function of lambda, and it's just minus the log of the 1, 1 element of this inverse Toeplitz matrix. So the Toeplitz matrix that's given from the point at which we evaluate the proximal operator. This is just a general Toeplitz matrix. We add to it a multiple of the identity that must make the sum positive definite. And then we take the 1, 1 element of the inverse. So that's a... so to solve this, we can solve it via the dual or solve a set of, solve the optimality conditions to get the dual multiplier. And then once we have the dual multiplier, we get the optimal solution. So this would be what typically the gradient of the dual function looks like. So it's a simple convex optimization problem. If we solve it by Newton's method, then at each iteration of Newton's method for lambda, we have to evaluate this function and its derivative. And to compute the derivatives, we have to evaluate the cost function, we have to compute this 1, 1 element of the inverse of this Toeplitz matrix as a function of the scalar variable lambda. And that can be done by Cholesky factorization of this positive definite Toeplitz matrix. And that gives us the value of the function, also the gradient, and then we can use that in Newton's method to find this optimal solution lambda, and then plug it in the optimality condition to get the optimal x in the projection. So the cost per iteration here would be order n squared for the Levinson algorithm, because that's gives you the Cholesky factorization of a positive Toeplitz matrix in order n squared. And actually there exist many methods that are even faster than the n squared. So in this case, it is true that the cost of this proximal operator would be reduced to order n squared if we just assume that the number of Newton iterations that are needed to solve this dual problem are roughly constant, and a small, you get a small multiple of order n squared as complexity of this Bregman proximal operator, as opposed to the n cubed that you get from the squared Euclidean distance. So this is a small example with an application where this typically might come up. So here we fit to some sample covariance matrix R, a Toeplitz matrix that's given by a Toeplitz matrix, positive semidefinite Toeplitz matrix of a variable y, a scalar S, multiple of the identity, and we try to fit a covariance matrix, a matrix of that form, to a sample covariance matrix R in Frobenius norm. The Toeplitz matrix must be positive semidefinite, and we add a penalty on the trace because we want this Toeplitz matrix to have low rank. So typically it comes up in signal processing in trying to estimate the parameters in a model like this, where you have a number of sum of exponentials, complex exponentials, and you're trying to estimate the number of terms and the position and the magnitudes of the exponentials. So you might get something like this, where from the sample covariance matrix, you have these 4 circles would be the exact location of the pulses, and then you try to find the harmonics by fitting a low rank Toeplitz matrix to the sample covariance matrix. And it illustrates so here we have the Toeplitz matrix constraint in the primal problem. The dual will involve a non-negative trigonometric polynomial, that's the solid line here, and complementary slackness will give us the relation between the two, the position of the harmonics that are related to the eigendecomposition of the primal solution T, the Toeplitz matrix, and then the dual polynomial. So we'll solve this problem by the dual, by the IGA methods, by Ausländer and Touboul. This is the convergence iteration, which is actually order 1 over k squared in theory and also here in this example. So this method is actually the IGA method by Oostlander and Mark de Boel from 2006. It's a Bregman extension of one of Nesterov's fast gradient projection methods, where we use the Bregman distance as an proximal operator. Here we use it to solve a problem of this form with a differentiable f and a convex set C. You need f to have a Lipschitz continuous gradient and d to be strongly convex. And it's possible to determine the step sizes and the parameters by a line search. That doesn't require you to actually know the strong convexity constants L and the Lipschitz constant L and the strong convexity constant, which is also important in this example. Right? So that's the method we'll use, and this actually gives us the complexity. Then we look at a simple problem where we actually do the Euclidean projection on this normalized set of positive semi-definite polynomials. We compare with the complexity of an interior point method called via CVX. So as expected, we're in the dimension ranges from up to several thousand. So as expected, the interior point method has a complexity of n to the fourth. With this IGA method and the Itakura-Saito distance, we have something that's almost n squared, actually a little bit less than order n squared. This is the total time, and this is the time per iteration. So that's actually the first application. Then the time that remains, we'd like to follow the same approach and maybe look at the other type of application that I mentioned in the beginning, where we look at sparse semi-definite optimization problems. Problems where C and AI are also very sparse. And we'll assume they're denote the sparsity pattern by E. So E is actually the union of the non-zero positions in all the coefficients. We can assume, actually, without loss of generality, that E is a choral pattern. So it's the permuted filled Cholesky pattern. And a problem in semi-definite optimization is that even when AI and C and all the coefficients are very sparse, X in general has to be dense to make the matrix positive semi-definite. So usually the most feasible solutions and the optimal solution will be dense, even when C and all the coefficients AI are very sparse. But there is a difference, or sparsity does matter, because if you look at the objective and the constraints, then it's also clear that you can actually distinguish two types of variables in the matrix X. So there are the variables, the entries in X that are multiplied with non-zeros in C and AI. And those are actually the real optimization variables that determine the value of the objective and determine feasibility and the equality constraints. And all the other variables that are not part of the sparsity pattern of AI or C don't really matter. They only have to you only have to make sure they exist to make the matrix positive semi-definite. So an alternative way of looking at this sparse SDP problem is to look at it as a conic LP problem, where like this. So it's almost just a matter of notation where we replace X. Here we optimize over the dense matrices X. In the second problem, we optimize over sparse matrices X with the sparsity pattern of the problem, of the coefficients AI and C. And the cone here is denoted by K. It's the cone of matrices, sparse matrices X that have a positive semi-definite completion. So it's a very minor difference, but the interpretation is very different. Here we have a very large scale problem very easily. So you have an n by n matrix X. Very quickly, the number of variables, order n squared, increases to a very high number. Here X is a sparse matrix. And even when n is large, it's a very sparse sparsity pattern. The number of variables in X could still be not necessarily very large. So it's not clear that even for quite large n, this is really a terribly large scale problem, right? But we have to deal with this cone of positive semi-definite completable matrices as a constraint. So we don't really have a good Bregman kernel for that cone directly. We can do something that's close, and we can look at the centering problem in semi-definite programming. So we will look at this problem with the sparse matrix X as variable, the cone of positive semi-definite completable matrices. And we look at the centering problem. So computing a point on the central path where phi is the barrier function for the cone. And then we just have equality constraints that come from the equality constraints in the problem. And the barrier function, the logarithmic barrier function for this cone of positive semi-definite completable matrices is defined like this as the conjugate barrier of the corresponding dual cone. So if K is a cone of positive semi-definite completable matrices, then the dual of that cone is the cone of sparse matrices that are positive semi-definite. We know the barrier function for that cone is just a standard log that barrier. The conjugate barrier is the cone of positives, is a barrier for the semi-definite completable matrices. So that's the one that's used here in this centering problem. So for finite positive mu, this gives us a suboptimal point on the central path. It's of course the basis of barrier methods for computing the solving the conic LP. If you do this for a decreasing sequence mu. But in a large problem, even for a finite small mu, this might give us an acceptable approximate solution of the sparse problem. Right? So as a kernel function, we'll use the barrier itself, phi. Then we'll have to be able to compute again, answer the same questions as in the first part of the talk. We have to be able to evaluate this function phi efficiently, its gradient, and then compute the projection using that distance. So the value of this barrier function for the positive semi-definite completable cone is related to maximum determined completion problem. So this is the definition of the barrier. The optimal S in the definition is actually the inverse of the maximum determined positive definite completion. So solving that completion problem gives us the value of phi. The solution S also gives us the gradient of phi. And in general, this is a convex optimization problem. But if we assume the sparsity pattern is choral, then there exist very efficient algorithms for computing this S, the completion, or the inverse completion, in very efficient algorithms and actually closed form solutions. And the complexity, that's the most important one, is roughly comparable to the cost of a sparse Cholesky factorization with the same pattern E. And the distance is actually related to the Kullback-Leibler divergence of matrices. And then we can compute the Bregman proximal operator with this barrier function for the centering problem in a very similar way as for the Itakura-Saito distance. Again, we introduce a normalization that can be done in different ways. So here we just normalize or assume the constraints imply also a constraint on the trace of the matrix. You could take trace of a positive definite matrix times X, or this could be an inequality to bound the solution set. And then again, to compute the Bregman projection with the barrier kernel, we have to solve, in this case, a problem of this form. X is the matrix variable, phi is the barrier of the positive semi-definite completable cone, and you have a simple single linear equality constraint. We'll solve it via the dual, and the dual would look like this. We maximize over a scalar variable lambda, the multiplier of the equality, this function, log that of b plus lambda I, where b is a positive sparse matrix, and lambda is large enough so to make this positive definite. So it's a convex differentiable optimization problem in a scalar variable lambda, but B is a very large sparse matrix. And the question is, how do we, what's the cost of solving this problem? So if we again do it by Newton's method to solve the optimality condition for the primal problem or to solve the dual, then we have to solve this nonlinear equation in the scalar variable lambda. So it says that the trace of the inverse of this positive definite matrix must be equal to 1. It's a very sparse matrix because B is sparse. And then from the solution, we get a solution of the projection. And if we assume the sparsity pattern is choral, then there exists efficient methods for computing all the quantities you need to in a Newton iteration for this, even when the dimension is very large. So you can actually easily compute the inverse, the trace of the inverse of the matrix without computing the full inverse very efficiently. We can also compute the derivative, which would be the trace of the square of the inverse. And then we can also compute from lambda the solution X, which would be the projection of the inverse on the sparsity pattern. So one iteration of Newton's method for this problem would have roughly a complexity that's comparable to the cost of just a sparse Cholesky factorization for that sparsity pattern. So that's something that scales to very large dimensions if the problem is sufficiently sparse. So maybe just to finish 2 examples. So we apply this to the first max cut problem, where we took 8 problems, 4 from SDP lib, and then 4 that we generated from sweet sparse. So these are the dimensions in. They're all very sparse. We compute a point on the central path of this problem with this barrier parameter. And actually for the values of the objective value, this was actually a very accurate solution almost to the original problem. We used the Bregman version of the Chambol-Poc or the PDHG method. And so these are the results. These are the number of iterations in the proximal method in the range in the hundreds, as is typical, I think. And the other columns show the cost per iteration. So this is the total time per first order iteration. And this shows that or tries to confirm the conclusion that the total time per iteration is roughly proportional to the time of a single Cholesky factorization of the same sparsity pattern. So this is the average number of Newton steps to compute the dual solution in the operator. This is a cost per of one Cholesky factorization of that sparsity pattern, and the product of the 2 is roughly the cost per iteration. And then this is a more other problem, the equipartitioning or SDP relaxation of graph equipartitioning, where we have a problem with that's less sparse, but we can still fit it in this form. Again, 8 problems, and it's denser, so the time is a little longer, but roughly it's still the same conclusion. So the cost per Bregman projection is roughly proportional to the cost of a Cholesky factorization. So we use the Chambol-Poc Bregman version of the Chambol-Poc method because the problem fits this form now with f and convex function. And this is actually a good form because this will include, if f is the indicator function of cones, also general conic optimization. But I'll skip the details here. And so this is a summary of the 2 topics we discussed with the references. So in both cases, the goal was to reduce the cost of the proximal algorithm by using a Bregman distance that matches the structure in the problem, and to avoid the cost of an eigenvalue decomposition that would be needed in the standard proximal method for the SDP problem. Thank you.
Thank you very much for this very nice talk with very nice illustrations. Yeah, in particular, considering some real life problems and motivated by engineering applications.
Thank you.
So it is time for questions. Are there any questions? Jonathan.
Yeah. So did you prove this, the convergence of Bregmanized Chambal-Pak? Is this known?
There's an ergodic convergence result that they, in this 2016 paper, they derived.
Okay. Okay, so it's okay. I wasn't clear. So the 2016 does already use a Bregman function.
That's the that's the Bregman
Okay.
version of the earlier Chambal-Pak method for proximal.
Okay. Because I mean, Chambal-Pak can be looked at. I mean, Chambal-Pak is actually DR. I mean, you can look at it as the original Chambal-Pak. You can look at as Douglas-Retford.
Yes, the
right
Bregman
norm.
is actually not that clear, I think, because the Okay, so this is the version that is sufficient for our purposes. They have the f of x plus g of ax, more general version that they discuss. Right? And you could have a Bregman kernel on the primal and the dual.
Right.
For our purposes, we actually only need, for the equality constraints, we just use the standard. This is the version with the standard Euclidean kernel for the dual variable, right? And it's only for f that we have a Bregman.
Yeah, well,
it also helps.
I mean, quadratic is Bregman, so yeah. So,
but it helps in the analysis also. It simplifies some.
But they only prove ergodic convergence. But you are using the actual point or using the ergodic point?
We use the actual point.
Yeah. Okay, so I have a second question, which is on the first application where you had a lot of Newton steps.
Sorry?
The first application, you had more Newton steps. I mean, you had like 10 Newton steps or something, right?
Yeah, it was a different implementation. It's a matter of, I think, the starting point. I think for the sparse SDP, we had a better heuristic starting point.
Right. So, but I think one thing to consider, you know, there's a whole literature of inexact prox methods.
Yeah, exactly.
So if there's some not too expensive way to check suboptimality of these Newton points, you may be able to truncate.
Yeah, that's important.
Yeah. So that's something we could discuss that offline, but that,
yeah.
I mean, I don't know if there's an inexact version of IGA. That's something you would have to derive. Yeah.
Yeah, we can ask Mark, right?
Yeah. Okay.
Yeah, thank you.
Thank you, Jonathan. Other further questions?
The answer is no.
Okay.
Well, maybe
Mark?
we should wait. Maybe we should try to make the answer yes, and then.
Please be my guest.
Okay.
I mean, actually, there's was the acceleration? Do you think that was critical to the performance of that method?
Oh, you can do some approximation also within accelerated schemes. That's possible.
Right.
There are some works that have been done in that area, but
yeah, but I'm just wondering in practice, you know, the acceleration feature might not be so critical in practice. So you could work with the regular forward backward, and maybe things would be a little simpler. Yeah.
Maybe.
Misha Kochwara?
Hi, Lieven. Just to clarify, on page 27 in the table, what would be then the total time for solution of, let's say, the GPP?
It would be the product of the last two columns.
Yes. Okay, yeah, thank you.
Yeah. And there are many parts in this calculation that can also be improved, but the main conclusion, I think, is that the cost per iteration is reduced to something that's very scalable.
Yeah. Thank you.
And there are, of course, possible improvements in the first order methods, and we can be very useful to look at inexact versions and so on. But the cost per proximal projection is roughly proportional to the cost of a Cholesky factorization with the same pattern. That was the the goal.
Thank you. Are there further questions? So then I have a question, Lieven. So in every iteration, instead of course of calculating this proximal step, you are just running an inner loop, like a Newton algorithm. And is there any chance to get a theoretical result? Yeah,
that would be
on the overall rate, let's say, of the scheme, or the. I mean, of course, this is something which Jonathan suggested to look at some algorithm, primal dual or symbolic with errors, and try to quantify errors and to see if the Newton doesn't destroy this condition. But probably there is something else.
Yeah, that would be very interesting. And I mean, it's similar. Even in the Euclidean case, many proximal mappings involve some search over a linear or a scalar variable, right? Like an even projection on the probability simplex or the L1 norm ball. So in that sense, it's similar. But we haven't analyzed actually the cost of the Newton algorithm for that scalar problem.
Okay. And so just to be clear, so the primal dual symbolic with Bregman distances. So for this algorithm, there is a rate, a primal dual rate, which is an ergodic result. Is this correct? Yes. So okay. Yes. But then it would be interesting to see if this rate is affected by the Newton iterations you are doing in every step. Yeah.
That's true.
Okay. Thank you. So if there are no other questions, I propose to stop here. Thank you very much for a nice talk, for a very clear presentation, and for the nice discussion. Thank you for being with us so early in the morning.
Yeah, thank you.
We are very thankful for a nice talk. We will post the.
You can go back to
video
bed.
and the slides.
Sorry?
Yes.
Even you can go back to bed now. That's okay. Your work.
We will post the video and the slides on the website. So, and I just want to announce that the next speaker will be Frank Curtis next Monday, same time, but a more convenient time for Frank, I guess. Yeah. So, have a nice week. Thank you very much.
Thanks.
Thank you.
More convenient for him.
Yes, for him. Bye-bye. So it was great. And so we had a solid audience, I would say, and many people in the room. Thank you.
Thank you. I'll send the slides, right?
Yes.
Yeah.
Okay.
Okay.
Bye-bye. Have a nice day. Bye-bye. Bye.